Hey guys, so this is a continuation of circular motion review. Let's quickly talk about Newton's law of gravity. So as we discussed in class, I want you to remember that gravity is a universal force that affects all objects in the universe. There's a gravitational force between you and every object around you. All right. So what does that mean? It means between two objects, they have a force. So this object has a gravitational force with this pencil. This object has a gravitational force with the book. With the Lizzie, these are all straight lines, not parabolas. With the Lizzie and the center of the earth. All right, they have this pencil has one with the book. This pencil has one with the center of the earth. This pencil has one with the Lizzie. All right, and the book has one with the center of the earth. The book has one with the Lizzie. Drawing a parabola on the straight line. Yes, and the Lizzie has one with the center of the earth. All right, notice that all of them are conjoined together somehow. All right, so that's just to tell you that between two objects, any ordinary objects, there's a gravitational force between them. And fortunately for us, Sir Isaac Newton gave us a way to calculate the gravitational force between these two objects. All right, so this is how we'll model it. That's how we draw it, basically. If I have an object 1, right, and I got an object 2. Isaac Newton told us we have to consider the distance. We need to know the distance between the two objects, as well as their masses. All right, so it's going to be mass object 1, mass object 2, in order to be able to get the gravitational force. And the formula for our gravitational force is Gm1 m2 over r squared. All right, now this is the formula. So G here is our gravitational constant. And that number is basically given by 6.67 times 10 to the minus 11. And the units are, I believe, let's do a quick search. Gravitational force units, I believe, Newton meters per kg squared, something like that. I could be mistaken there, but no worries. And this is the mass of object 1, mass of object 2. And then this is the distance between the two objects. Yes. So you remember that? So remember the image I drew, the function I drew for you guys in class? I basically showed you that gravity is a 1 over r squared force, basically. And 1 over r squared forces, a characteristic of 1 over r squared forces is that the further the two objects are, the less force there is. So notice if r gets big, Fg becomes very small, all right? And that's shown by this thing. As the bigger r is, the smaller Fg is. The less r is, the bigger Fg is, all right? So they're very affected by their distance. And that's a key fact you need to know for your AP exam to help you peruse through multiple choice questions that involve Fg equals Gm1 m2 of r squared, our gravitational force. All right. So if calculate the gravitational force between two people, here's the question is basically saying that we have two people, so next to each other, and they have equal mass. Mass 1 is going to be equal to 65 kg. Mass 2 is also 65 kg. It's your average students. And the distance between them is 0.6 meters. Oh, this is a very easy question. All you got to do is plug in your values. All right. Solve it and tell me what you get. All right. Solve it and tell me what you get, guys. Just plug in the values into the equation and tell me what you get. I know some of you probably want me to just tell you what it is, but okay, fine, I'll tell you. It's 4.7 times 10 to the minus 7. All right. This is a very small number. Very small number. All right, so that's to tell you the key fact that the gravitational force between two objects is negligible when both of the masses are ordinary, like average sizes. All right, so this is a fill in the blank kind of thing that I made. It says there is a gravitational force between all objects and the universe, but the gravitational force between two ordinary sized objects is negligible. And this is mainly because they just produce a small force. Gravity only becomes a force worth considering when at least one of the masses are huge. A good example is between you and the Earth. Think about it. Like, what's the mass of the Earth, right? Mass of Earth. I'm looking it up right now. It's so large. Yes, 5.972 times 10 to the 24th kg. All right, let me write this like this. Sorry, apologies. Yeah, it's so huge, and this is your mass, approximately, or average person's mass, 65 kg. So if I calculate my force of gravity between the two of you guys using GM R squared, let's see, what's the distance between the land and, let's see, R, what's the distance between the land, between us and the center of the earth? Let's see, R, let's see, basically the radius of the earth. So yes, I'm looking up the Earth's radius. The radius of the Earth is 6,771 kilometers. I want it in meters because it's going to be in SI. So this is basically going to be almost 6 million meters. Still big. So I'm just going to say 6.3 times 10 to the power 6, approximately. So if we put this in our formula, if we want to calculate this, it's going to be 972 times 10 to the 24th. We're going to have 65 kg of the student who we're talking about. And we're also going to have the gravitational constant, 6.67 times 10 to the minus 11, right? And then we divide it by the radius squared. Could I have done my conversion wrong? I don't think so. 6.3 times 10 to the power 6 squared. And this is going to be approximately a very big number. All right. And because this is very big, this is a big reason as to why we as people are just submerged into, like, we can't fly, we're not floating. It's because of this gravitational force between us and the Earth. All right. Anyway, let's look at free fall acceleration. So as we've already established, the force responsible for our weight is the gravitational force between us and the Earth. And how we have quantified that so far, if an object is going down, we have used the weight. So if weight is going to be equal to mg, and remember, we qualified that we have different weights on Earth and away from Earth. So I want to say my weight Earth is going to be equal to my mg Earth. But today we've learned another way to measure the force of gravity on an object, in fact, between two objects. Mg Earth here is going to tell you the gravitational force on the Earth. But another way to say that is the gravitational force between the Earth and you. And you, it's the same thing, all right? This is the letter U. And that's going to be equal to G, mass of the Earth, mass of you, over R squared, all right? So this is mass of the Earth, yeah. And because they're both measuring gravity, right? The pull of gravity on you, on a person, on an object in the Earth, these two formulas are equivalent, all right? So I can simply plug in Fg Earth on you for a W Earth. So if I go, I say Fg Earth on you to be equal to weight Earth, right? I can plug in the formula GME mu over R squared. I know here I'm using the Earth and U, but you can really just ignore the subscripts because this applies to all planets. Mg Earth. The ME's will cancel, right? And we'll be left with G Earth is going to be equal to G mu over R squared. Apologies, I think I mixed this up. This is supposed to be mu. Okay, anyway, yeah, this is supposed to be mu. Apologies, mu. So it's not the me that cancels out. Apologies, it's the mu. And why it's supposed to be mu is because we want to measure the gravitational pull on you. All right, so that's why we are changing that. This is me, so M mass Earth. So look, wow, we have developed a formula to measure free fall acceleration. So on Earth, what do we expect G to be? We expect G to be 9.8. 9.8 meters per second squared. You should try it, all right? And I want you to try it. I have some formulas here. Try to measure the gravitational acceleration on Earth, and also try to measure the gravitational acceleration, rather instead of measure, let me say calculate, on the moon. So basically, what I'm trying to emphasize is that this formula here, G equals the gravitational constant times mass of a particular planet times the radius squared of the planet will tell you the free fall acceleration on that planetary body. All right, so I'll just say G planet, well, mass planet and the radius of the planet. This will tell you the gravitational acceleration on that body. And here I say planet, but it can also work for the moon, so long as you have a really, really large mass, all right? So basically a celestial body. It works for all celestial bodies. So yeah, you can measure the free fall acceleration on Jupiter if you know its mass and radius. And these are all things you can just look up and try to measure. So yeah, very important to know this formula. So yeah, and that's the video. Here's my summary. of Newton's law of gravity. I hope you enjoyed this video, guys, and yeah, good luck.